The Optimode is a device developed and produced by SRA Instruments with the goal to exploit the full potential of thermally modulated GC times GC. Thermal modulation is perhaps the most common and widespread approach to GC times GC. The process is based on temperature by means of gas streams that we call jets. The cold jet will create a cold spot on the column to ensure the molecules will be effectively trapped. The hot jet will, on the other hand, ensure a rapid and effective remobilization into the gas phase. The process is a dual-stage one to maximize the refocusing power of the technique. The rapid and effective thermal process produces a very narrow injection band. As a consequence, modulated peaks will be symmetric and very sharp, with beneficial effects on chromatographic resolution. Thanks to these features, we can say that thermal modulation is arguably the golden standard for GC times GC in terms of performance and flexibility of operation. The Zoex Loop thermal modulator is one of the most well-known products on the market in the field of GC times GC. The Zoex modulator will achieve a dual-stage refocusing process by minimizing the hardware. In fact, only one cold jet and one hot jet will be necessary. This thanks to a capillary column segment coiled as a loop in a dedicated support, which will make sure that molecules in their elution through the analytical columns will encounter each jet twice. With the first cycle, molecules eluting from the primary column will be focused and then released into the loop, which will effectively act as a delay path. During the second cycle, the molecules will be refocused a second time and then reinjected into the second dimension. With this configuration, the cold jet is always on, while the hot jet will periodically pulse at a timing controlled by the user. Here an example of standard configuration for a GC-GC system with Zoex modulator. This kind of platform is very effective, especially for volatiles and semi-volatiles, but will grant excellent performance for a very wide range of applications. The cold jet flow is regulated by a needle valve and will be set at a constant flow during the run. Modulation period and hot jet pulse will be manually set thanks to the programmable logic controller installed on the side of the GC. Like for any thermal modulator, we need to take into account a significant consumption of gas for the jets, in the order of several liters per minute. In addition to this, if we do not use a refrigeration unit for the cold jet, but a Cryotrap bath model, we also need to take into consideration the significant use of liquid nitrogen. Also, the value of the cold jet flow is very important for a correct operation of the modulator. If this is too low, we might have possible breakthrough of volatiles. If it's too high, we might have inefficient remobilization of the heavy compounds which are trapped too effectively. The SRA Optimode can be installed very simply in line with the standard Zoex configuration to enhance the control over the modulator itself. A mass flow controller will give us more precise control over the cold jet flow. This way we can optimize the cold jet flow during any run. Also, a standby mode will help us to reduce operational costs. The hot jet is also fully controlled by the Optimode in terms of hot jet pulse and modulation period. The interface is very simple and intuitive. Thanks to these features, the Optimode is a very powerful tool to maximize the performance of Zoex modulator and also reduce costs. It can be installed at the beginning with the Zoex modulator itself, but it's also possible very simply to upgrade any existing system. Let's see more in detail how the Optimode can be beneficial to the cold jet. The gas flow will be controlled by a mass flow controller. This will enhance reproducibility and flexibility. Moreover, the flow value will be now programmable within the run. We can in fact set a higher flow value at the beginning of the run for the volatiles, which will require a higher volumetric flow for efficient trapping. The heavy compounds will not require such a high cold jet flow to be trapped. Therefore, we can reduce the cold jet flow during a run. This way, we can achieve an optimized value across a very wide volatility range. Several ramps are also possible. In addition, we have the possibility to set a standby flow between runs. The volumetric flow can be reduced from the operational rate, typically between 15 and 20 liters per minute, to a minimum value. This will prevent freezing of the transfer line, while at the same time reduce consumption of gas, as well as liquid nitrogen if we use the model based on cryogenic cooling. Also, the Hotjet valve will be fully controlled by the Optimode. The hot pulse duration and the modulation period will be fully controlled and programmed by the software interface. We can program the Hotjet pulse duration across the run. We will in fact need a shorter pulse for the volatiles. We will be easy to remobilize, while perhaps we need to set a more intense Hotjet pulse at the end of the run for the heavy compounds. The multi-modulation mode will make it possible to set variable modulation periods across the run, with beneficial effects on the chromatographic resolution. Here an example of the web browser interface. The Optimode offers excellent performance thanks to the state-of-the-art electronics and pneumatics. This is essential to obtain consistent images and high reproducibility and repeatability among sequences. Now, a practical example of performance enhancement. What does it mean for your chromatography? On the top, an unmodulated peak with a baseline of about 9 seconds. If we apply a modulation period of 4 seconds, we expect 2 theoretical modulated peaks. You can see here that with the initial settings for cold jet flow and hot jet pulse, this does not happen. We have 7 modulated peaks. This is the effect of poor remobilization. The hot jet does not manage to transfer all the trapped molecules efficiently. Therefore, these stay behind, and we have an inefficient transfer into the second dimension. As a result, we have a number of modulated peaks, which is not what we expect, and also a very poor peak shape in the 2D, as you can see. Now, there are 2 ways to solve this. We can reduce the cryogenic trapping, or we can enhance the remobilization by using a longer hot jet pulse. As you can see, both independently work. We can also use them at the same time. In this way, we have the correct number of modulations as well as an excellent peak shape in our 2D chromatogram. We can now investigate the optimization in performance across a wider volatility range. In this case, we used a standard mix of linear paraffins in the range from C5 to C28. On the left side, you can see an unmodulated chromatogram. First of all, if we want to be able to efficiently trap the lightest compound, we need to determine the minimum cold jet flow necessary to do so. Here you can see that simply by decreasing the cold jet flow of a small value, we are losing trapping power. It is therefore key to test this and use the appropriate cold jet flow. We can now see the raw data for the chromatogram obtained by applying this cold jet flow and a standard hot jet pulse of 250 milliseconds across the complete volatility range. At the beginning, modulated peaks look good. Increasing the carbon number, we see the peak shape starts to get poorer and poorer, and at the end, peaks are completely missing. This is because the hotjet flow under these conditions is not able to remobilize the material which has been previously trapped by the cold jet. Now on the right side you can see the profile that we obtained by optimizing the cold jet flow. We start with the value we found necessary to effectively trap pentane, and then we can linearly decrease. In this case we have two different windows with different rates in order to ensure that we are not applying too much cold flow for the higher boilers. At the end, we can set a standby flow to save gaseous nitrogen. By doing so, we obtain proper modulation. You can also see in the table that if we compare the number of modulated peaks we obtain in practice with the theoretical expected number of peaks, we have a perfect match. We can of course also visualize this as a typical 2D plot. You can see here on the left side the not optimized chromatogram, and on the right side the optimized chromatogram, which shows excellent peak shape across the complete range. Here an example of actual application for the Headspace analysis of foodstuff, in this case Headspace SPME of roasted coffee. As you can see, even for very volatiles, we have extremely sharp peaks, the chromatography is excellent, and we have very good resolution for this complex and very volatile area of a real life sample. Here, another very nice example that shows how the flexibility of the Optimode can be exploited in a very clever way to extend applicability. Here, the Optimode is also used to program the modulator to act as a cryotrap at the beginning of the run. This is achieved by installing a pre-column as a third loop, the Zoex modulator loop holder, and by programming the Optimode with the cold jet on the first couple of minutes of the analysis. In this way, we are effectively refocusing the analyzed dissolved by the fiber to achieve a good peak shape. Here we can see a couple of examples of what this means by focusing on the peaks of XNL and XNL. You can see on the left the refocus peaks, which are characterized by a very good peak shape. On the right side, you can see the peaks we will obtain if we don't perform the refocusing. As you can see, these are characterized by severe tailing over the first dimension. This tailing is not present when using the Optimode to refocus the peaks through the modulator. And finally, an announcement. We are currently working on the new Optimode Plus. This will be based on the same proven technology of our current Optimode to grant you excellent precision and reliability, but it will come with a new and improved user interface to extend applicability. We will in fact implement the possibility to build sequences with different methods. This way, you will have full control over all your modulation parameters, flow and times, not only during your run, but with methods and sequences across several runs. This will then allow you to perform effective and fully automated method development and optimization. In summary, the SRA Optimode is a very powerful and flexible tool to get the best performance out of your thermal modulator. You will gain full control in order to optimize performance. At the same time, it will give you the chance to save resources such as energy, gas, and liquid nitrogen if you have a cryogen-based model, in order to reduce cost and also minimize environmental impact. All controlled by a user-friendly software interface. If you want to know more, don't hesitate to visit our website or contact us.